If we just had to use the power rule, then we'd only have x to a power. So how do we get to taking derivatives of polynomials? Well, we get from the power rule to taking derivatives of polynomials using these two rules here. Now, these two rules don't work just for polynomials, but they're going to be easiest to see in polynomials. So the properties of derivatives, it turns out, are, well, we have two properties of derivatives. One is called the sum difference rule. And that says if you take a derivative of two functions, added or subtracted, then what we can do is we can split it up and take the derivative of the first piece plus or minus the derivative of the second piece. This is really handy when I have a polynomial with like 2 or 3 or 4 terms, because then that means I can take the derivative of the first term, derivative of the second term, and just keep going about that way. The other rule that we have is the constant multiple rule. And that says if you have a constant number, c, multiplied times a function, and I want to take the derivative of that, then it's just going to be the constant number multiplied times the derivative. So these are really nice rules. The sum difference rule and the constant multiple rule allow me to take lots and derivatives. Now, we can do this function using the sum difference rule and the constant multiple rule. In fact, I alluded to it in a previous video. We have x squared plus 3x minus 2. So that means I have 3 terms. I can take the derivative of the x squared component. That, using the power rule, is 2x. I can take the derivative of x. Now the derivative of x is 1. We have a constant multiple of 3 out front. So the derivative of x, I know from the power rule, is 1. Since we have a constant multiple of 3 out front, 3 times 1 is 3. And then the derivative of a constant of -2 is 0. So I can take the derivative of this part, 2x to the first, the derivative of this part, which is just 3, and the derivative of -2, which is 0. So that's kind of how the sum difference rule and the constant multiple rule work. Let me show you how to do this with these two functions. So we have f of x is equal to a polynomial, and q of x is equal to the sum of 2 different types of functions. One is a trig function, one is the natural log. Let's take the derivative of the polynomial first. So in this case, capital F prime, the derivative of capital F, is going to be equal to. Now, normally in the power rule, we would take the 3 out front. So we get 4 times 3 times x squared. So I can take the derivative of this term. This term has a constant in it that I can pull out. So it's 4 times the derivative of what I get from the power rule, plus 5 times, you know what, I can do that. I don't know which times sign you like. Sometimes I use the cross, sometimes I use the dot multiplication. Guess I'll use the dot multiplication here. And so what we get is 4 times 3x squared plus 5 times 2x to the first minus 10 times 1 plus 0. And usually we will skip that step once you've seen it once or twice, and we'll simply write the final answer as 12x squared plus 10x minus 10. So usually we write the final answer like that. And once you get used to this, you don't write the middle step here. That happens in your head. 3 times 4 gives you 12. 2 times 5 gives you 10. Minus 10 times 1 gives you minus 10. Now, how about q of x? We take the derivative of sine. Well, 5 times the derivative of sine is going to be 5 times cosine of x. In essence, the constant just stayed in front. The derivative of natural log of x is 1 over x. And that's the entire problem. The derivative of q is equal to 5 cosine x plus 1 over x. Let's look at some other functions that we may not think fit our rule, or at least the rules that we've seen, but actually do fit the rules that we've seen if I'm willing to rewrite them. This is another common thing. A lot of people will see these rules and only interpret them a certain way, but we can rewrite these functions in order to fit our rules. We're going to do that with h of x is equal to 12 over x to the 5th. We'll do that with r of x is equal to 10 times the square root of x. And we'll do that with natural log of x, or excuse me, L of x is equal to natural log of x to the 7th. Let's take h of x is equal to 12 over x to the 5th. That does not look like something that I can take the derivative of yet. However, if I remember my exponent rules, dividing by x to the 5th is the same as multiplying times x to the negative 5th. So dividing by x to the 5th is the same as multiplying times x to the negative 5th. When you take a derivative, if I write 12 times x to the negative 5, what I can do is I can use the power rule. Even though this is a negative, the power rule works just fine with a negative. So negative 5 times 12, negative 5 times 12 is negative 60. And then x is going to be raised to the negative 6th power. So 1 less than negative 5. Remember, be careful that when you're subtracting 1 from a negative, we're getting further away from 0. So negative 5 minus 1 becomes a negative 6. So that's the derivative, negative 60 x to the negative 6th power. Some books will rewrite that. Some books will write that as negative 60 divided by x to the positive 6th power. It doesn't matter which way you write it for me. If Moodle says to write it one way, make sure you write it one way. If Moodle says to write it the other way, just make sure you write it the other way. But that's the derivative. As a word of caution, a lot of times people will write these things out and they will make the mistake of saying that the derivative is equal to the rewrite. That is not the case. So just be wary of that. The derivative is not the rewrite. So we have two things going on here. We have the rewrite, and then we have the derivative. So the derivative is not the rewrite. The rewrite is the function itself. And that causes, I can't tell you how much enormous problems that causes students every semester. So make sure you write the rewrite and then take the derivative of the rewrite. Knowing that, we can move on to this r of x. Now, the r of x, I'm going to write the rewrite of r of x underneath. Notice that my r of x is still r of x, not r prime. So I got 10 times square root of x. Well, the square root of x is x to the 1/2 power. If I take a derivative of that, well, that fits in the power rule notation. So 10 times 1/2 times x to the exponent, which is 1/2 minus 1. Now, 1/2 minus 1 is -1/2. So I am going to take my derivative and clean that up a little bit and call that 10 times 1/2 is 5. X to the 1/2 minus 1 is actually -1/2 or -0.5. If you use decimals or fractions, it's fine with me. So 5x to the -0.5 power or 5x to the -1/2 power. Again, don't get confused between the rewrite and the derivative. The rewrite is the function just written a different way. The derivative is telling you the instantaneous rate of change. Lastly, I'm going to take L of x and do a rewrite. If you remember your rules of natural logs, this will be straightforward. You can just take 7 times the natural log of x and know that that's the same thing as natural log of x to the 7th. With natural logs, exponents can be brought out front as long as we have a single term here. So as long as we have just x to a power, we can bring that power out front. And now I can say that the derivative of L of x is just a constant times the derivative of a natural log. So I take that constant of 7 and I times it by the derivative of natural log, which is 1 over x. And if you want to sort of make that derivative look nicer, well, that is just 7 over x. So the natural log of x to the 7th has derivative, which is 7 over x. We'll see another way to do that later on in this course. You can see here, though, how nice understanding some of your algebraic rules is. Understanding exponent rules with roots and negative powers, and then understanding how to manipulate natural log functions. These tools, these algebraic tools, are very handy when taking derivatives because we can algebraically manipulate stuff in order to fit the rules that we already know. What I'd like you to try is to try to find the derivatives of the following two functions utilizing some rules you know about exponents and using some rules you know about how to rewrite functions.